The world of chip design, it's traditionally been this highly specialized, pretty intricate field, right? But it's undergoing a really profound transformation.
It really is. Quite something to watch.
Yeah. And today, we're diving deep into how large language models, LLMs, are literally helping to build the future of hardware.
Uh-huh.
Our mission in this deep dive, basically, is to unpack how AI is getting right into the core of silicon development. We're talking generating code, speeding up verification.
Crucial stuff.
Exactly.
Yeah.
So you're about to discover what this LLM-aided design really means and, well, how it's set to pretty much revolutionize an entire industry.
It's a fascinating convergence, isn't it? Because, AI can seem quite abstract, but application here is incredibly tangible. Like, you can really see the results.
Tangible how? What are we seeing?
We're talking direct gains in productivity, a real reduction in design costs, and it's all by automating tasks that used to be just painstakingly manual. Super time-consuming.
Right, like the real grunt work sometimes.
Exactly. Some early research, for example, suggests LLMs could cut down that initial RTL code generation time by maybe 30% on complex projects.
30%? That's huge.
It is. That translates into weeks saved, literally. It frees up engineers to focus on, the breakthrough innovations rather than just repetitive coding.
Okay, let's unpack this then. When we talk about LLM-aided design, what exactly are we referring to? I mean, how do these language models actually engage with designing a chip?
Well, at its core, it's sort of about leveraging the LLM's ability to understand natural language instructions.
Mm-hmm.
Plain English, and then translate those into formal descriptions. For hardware, this very often means generating code in hardware description languages, HDLs. You've probably heard of Verilog.
Yeah, Verilog, HDL.
Right. So imagine describing what you want a chip component to do just in words, and the LM then writes the intricate digital logic for it, almost like having an expert assistant right there.
So it's not just writing essays then. It's actually writing the blueprints for electronics. That seems incredible.
It really is. Abstract language directly informing concrete hardware.
So how disruptive is that for the traditional ways of working? And where exactly does this fit into the typical chip design flow?
Oh, it's extremely disruptive.
Yeah.
But, in a good way, mostly. It primarily impacts what's known as the register transfer level, or RTL.
RTL.
Yeah.
Yeah.
This is the stage where engineers define the data flow and the storage elements within a digital circuit. It's really fundamental.
And before LLMs.
Before LLMs, this was a highly specialized, often very manual coding process. You needed deep knowledge of the HDL syntax, the hardware architecture.
Yeah.
It took a lot of time and expertise.
Yeah.
Now, with LLMs, the speed up in generating this RTL code, just from those high-level natural language descriptions, it's significant, really significant.
Can you mention quality too?
Yeah, exactly. Some research even shows that fine-tuned LLMs models specifically trained on hardware data can generate higher quality Verilog code in some cases, which is absolutely critical for complex designs. Even tiny errors at this stage can be, catastrophic later on.
Okay, that brings us right to the core question then.
Yeah.
How? How exactly do these models make that leap from just words, natural language, to functional Verilog code? Is it just magic, or is there a systematic method?
It's definitely not magic, though. I admit it can feel pretty close when you see it working well.
I bet.
The method often follows a kind of divide and conquer approach. You wouldn't just ask the LLM to design an entire complex processor from scratch in one go. That's usually too much.
Okay, makes sense.
Instead, you break the big system down into smaller, more manageable functions or modules, little building blocks.
Right.
And then you prompt the LLM, you give it instructions to generate the Verilog code for each of these smaller pieces individually.
Can you give us an example? Like, what kind of smaller pieces are we talking about here?
Sure. Think about specific logical operations or maybe computational blocks that get used repeatedly within a larger chip design.
Okay.
For instance, in a complex algorithm, maybe like signal processing or crypto, you might have a module that performs a specific type of bit rotation, or maybe a particular combination of logical ANDs and ORs.
Gotcha.
So you could ask the LLM something like, create a Verilog module that takes 32-bit inputs, let's call them A, B, and C, and produces an output D, where D is the result of A, XOR, B, and DC. You specify that logical relationship.
Okay. Very specific instruction.
Exactly. And the LLM can then generate that specific Verilog module for you. It's like having this ultra-fast draftsman who takes your high-level functional descriptions and quickly sketches out the precise digital blueprints for each component.
So it sounds like, a highly intelligent assistant. It writes the foundational code, maybe the boilerplate boilerplate stuff, but then you, the human engineer, still have to oversee it, refine it, check it.
Precisely. Absolutely. While LLMs can rapidly generate architectural ideas in that initial RTL code, the engineer's role remains completely crucial. They're not out of a job.
Good to hear.
They still need to deeply understand the underlying architecture. They need to be able to read, verify, and yes, sometimes fix the code the LLM generated.
So the goal isn't replacement, it's amplification.
Exactly. Amplify productivity. Allow engineers to focus on the higher level architectural decisions, the system integration, the really tricky verification challenges. Think about it. Engineers used to spend so many hours just hand coding these relatively basic modules. Sometimes it felt like they were just, highly paid copy pasters.
Huh. Oh, I've heard that sentiment.
Now, they can potentially offload some of that to an LLM. That's a massive psychological shift, too, not just a productivity gain.
That's a great point. But does it introduce new challenges? Like, if the code isn't human-written initially, is debugging different?
It does shift the focus, yeah. You might spend less time debugging simple syntax errors because the LLM often gets that right, assuming it's well-trained. But you spend more time verifying the logic that the LLM created. Does it actually do what you intended? Does it handle edge cases correctly? That requires maybe an even deeper understanding of the system's overall intent and potential pitfalls.
Interesting. So beyond just writing that initial code, what else can LLMs do in the hardware workflow? Are they sort of one-trick ponies for code generation, or do they help out in other areas too?
Oh, they absolutely extend beyond just code generation. Definitely not one-trick ponies. LLMs are proving incredibly useful in the verification process as well.
Verification. Okay, that's always a huge part of chip design, right? Takes a ton of time.
A massive part. Often the majority of the time and effort, actually. Right. So, for instance, LLMs can assist with testbench creation.
Testbench creation.
Mm-hmm.
Okay. You mentioned test benches briefly. Remind us, what exactly does a test bench do, and why is speeding that up such a big deal?
Right. So a test bench is essentially this sophisticated software environment you build specifically to simulate and thoroughly test your design hardware before you actually manufacture it.
Okay. Like a virtual proving ground.
Exactly. It applies specific inputs, we call that stimulus, and then it meticulously checks if the circuit behaves exactly as expected, down to the timing of every signal.
And that's hard to create.
Traditionally, writing all those stimulus patterns, figuring out all the input combinations needed to really stress the design and find bugs, that's a painstaking, often manual task. It requires deep insight into the chip's expected behavior and potential failure modes.
I see. And LLMs help here how?
LLMs can generate many of these stimulus patterns much faster, often just based on the design specifications or even the RTL code itself. They can explore the input space more systematically or generate random but constrained patterns. This is a significant time saver in functional verification, making sure the chip actually works as intended, catching bugs before you spend millions on manufacturing silicon.
Wow, okay. Reducing bugs before tape out. That's a game changer.
It really is. Finding bugs in silicon is incredibly expensive. Finding them in simulation is much, much cheaper.
And what about security? You touched on that earlier. Enhancing hardware security sounds absolutely critical, especially these days.
Yes, that's another hugely important and actually quite exciting area. LLMs have the potential to extract security properties directly from vast amounts of documentation.
How does that work? Reading manuals?
Sort of. By analyzing huge volumes of text design specifications, data sheets, academic papers, even past vulnerability reports describing the chip's functions and its intended security posture, LLMs can help identify potential vulnerabilities.
Like finding gaps in the design description.
Exactly. Or maybe identifying design weaknesses that match known attack patterns. They could also highlight specific security features that need extra rigorous verification. The idea is to significantly enhance the overall security posture of the final silicon, making chips more robust against attacks right from the design stage.
That's fascinating. But I imagine that also raises questions.
Oh, absolutely. This is very much an active area of research. You have to worry about, well, is the LLM itself secure? Could the training data have been compromised? Could the LLM inadvertently introduce vulnerabilities while trying to help? Ensuring the generated code or the identified properties are fully auditable and trustworthy is paramount.
Right. You need verification for the verifier, almost.
In a way, yes. You need robust processes around using these tools for security applications.
Okay, this all sounds incredibly powerful, but it's still a bit abstract. To really get a handle on it, could you walk us through a concrete, real-world example, maybe a complex algorithm, where LLM-aided design really shines?
Absolutely. A great example is something like SHA-256.
SHA-256,
Yeah.
the hashing algorithm
Yeah.
used in crypto, Bitcoin.
Exactly. It's fundamental. Core to things like digital signatures, ensuring secure transactions online, and yes, famously, Bitcoin mining. It's a perfect candidate for hardware implementation because it's computationally very intensive, and speed matters a lot.
So what makes SHA-256 such a good illustration for LLM assistance? Why is it important?
Well, SHA-256 has specific properties that make it secure, but also complex to implement correctly in hardware. First, it's designed to be one way you hash a message, but you can't easily reverse the hash to get the original message back.
Right, the security aspect.
Then there's the avalanche effect. Even a tiny change in the input message, like flipping a single bit, leads to a massive, completely different, unpredictable change in the final hash output. This makes tampering obvious.
Okay.
It's also deterministic. The same input always produces the exact same hash. And it's incredibly collision resistant. The chances of two different inputs accidentally producing the same hash are astronomically small. We're talking 2 to the power of 256 possible unique hashes. That's a staggeringly huge number.
Mind-bogglingly large.
It is, and think about Bitcoin mining that really highlights the need for hardware. It's essentially this global race to compute trillions upon trillions of SHA-256 hashes every single second.
Trillions per second.
Oh yes, miners take transaction data, the hash of the previous block in the chain, a timestamp, and they add a random number called a nonce. They hash all that together using SHA-256. Then they change the nonce slightly and hash again over and over, trying to find a hash result that happens to start with a specific number of leading zeros.
Just brute force, searching for a lucky number.
Pretty much. The first miner to find such a hash wins the block reward, currently 6.25 bitcoins, awarded roughly every 10 minutes on average. This massive computational demand is precisely why people develop specialized hardware, like ASICs or FPGAs, just for SHA-256 acceleration. Software on a regular CPU just can't compete.
Okay, so the need for specialized, fast hardware is clear. How do LLMs help actually design something that intricate for SHA-256?
Right. Implementing SHA-256 correctly in hardware it's a classic engineering challenge and involves a very detailed sequence of operations. Well, first, you have to precisely prepare or pad the input message. Convert it to ASCII bits, append a 1-bit, fill with zeros until it's a certain length, and then reserve the last 64 bits to encode the original message's length. Very specific formatting.
Okay, sounds fiddly.
It is. Then you take the message in 512-bit chunks. Each chunk is initially treated as 16 words of 32 bits each. You have to expand these 16 words into 64 words using what's called a message schedule. This involves specific bit rotations, shifts, and XOR addition operations functions, often referred to as sigma 0 and sigma 1 in the SHA-256 standard.
Lots of bit manipulation.
Exactly. And finally, there's a main compression loop. This loop runs 64 times for each 512-bit input block. Inside this loop, there are 8 32-bit working registers, usually labeled A through H, that get continuously updated. The update logic uses various nonlinear logical functions, the standard calls them choice, C, a majority, plus those sigma functions, the message schedule words we just generated, and a set of 64 predefined constant values specific to SHA-256.
Wow. Okay, that sounds intense. Very specific, very sequential.
It is. It's like building this incredibly complex Lego model where every single tiny piece has to be in exactly the right place, performing a very precise mathematical or logical transformation at exactly the right time. For a human engineer to design all of that from scratch, writing out all the Verilog code correctly, it's a significant undertaking. It's error-prone, and frankly, it can be incredibly tedious for some parts.
I can imagine. So the LLM steps in how?
Well, with an LLM, you can use that divide and conquer idea again. You can prompt it to generate the RTL Verilog code for individual components.
Like the choice function or the padding logic.
Exactly. You could say, generate a Verilog module for the SHA-256 choice function operating on 3 32-bit inputs. Or write the Verilog for the initial hash value register initialization. Or even describe a stage of the message schedule expansion.
So you break it down logically.
Yes. The LLM can act as that super fast draftsman again. It takes these high-level instructions or descriptions of the standard steps and drafts and an architectural starting point for each of those intricate components. It's truly amazing how quickly it can generate that initial structure.
And then the engineer takes over?
Right. It allows the engineers to jump much more quickly into refining the details, optimizing for performance or area, and crucially, verifying that the generated code correctly implements the standard. They're not spending those first long hours just writing hundreds of lines of fairly repetitive, albeit complex bit-level logic from scratch.
So it accelerates that initial, maybe more tedious part of the design.
Dramatically. This ability to break down a complex problem like SHA-256 and quickly generate plausible initial code for its subcomponents, that's really where LLMs are starting to shine in hardware design. It speeds up that early design phase significantly.
Okay, it really does sound like LLMs are poised to, well, revolutionize chip design. But we touched on challenges earlier. What about the hurdles? Beyond the technical capabilities, what are the big roadblocks or concerns in this emerging field?
Yeah, it is still an emerging field, and you're right, it absolutely requires thorough examination and caution. One critical area we mentioned is security and privacy, especially when LLMs get involved in designing sensitive hardware.
How so?
Well, the models themselves, or perhaps the vast datasets they were trained on, could potentially introduce vulnerabilities. Think about it. If the training data included proprietary design information or even flawed code examples, could the LLM inadvertently leak intellectual property or replicate those flaws in new designs?
That's a serious concern. IP leakage.
It is. And then there's the challenge of auditing and trusting the LLM-generated code itself. Can we be absolutely sure it's correct, that it's secure? Or are there subtle biases or maybe weird edge case behaviors introduced by the model's black box nature that a human reviewer might miss?
Right. How do you formally verify code that wasn't written with human intent in the same way?
Exactly. This really necessitates developing robust validation frameworks. We might even need new formal verification techniques specifically designed to analyze and prove properties about AI-generated hardware designs. Making sure these incredibly powerful tools are used responsibly and securely is, well, it's an active and absolutely crucial area of ongoing research and development.
That's a profound consideration. It really changes the game. So, boiling it down, what does all this mean for the future of hardware engineering as a discipline and for the engineers themselves?
I think it means the role of the hardware engineer is definitely evolving significantly.
Hi.
Well, the foundational knowledge understanding, chip architecture, digital logic, timing, verification principles, that remains absolutely paramount. You can't prompt an LLM effectively or verify its output if you don't understand the fundamentals yourself.
Right. You need the expertise to guide the tool.
Precisely. But engineers can increasingly rely on these powerful AI tools to handle more of the, let's say, repetitive or intricate low-level coding tasks. The stuff that takes time but maybe isn't the most intellectually stimulating part of the job.
Freeing them up for?
For focusing on higher-level architectural innovations, system-level optimization, thinking about power efficiency, overall performance, ensuring the security and integrity of the entire chip. It's about empowering engineers to tackle more complex problems and innovate faster because they're not getting quite as bogged down in those lower-level implementation details.
So the skill set might shift a bit.
I think so. The learning curve might become less about memorizing every detail of Verilog syntax and more about learning how to craft effective prompts for the LLM, how to critically evaluate and verify AI-generated outputs, and how to integrate these tools effectively into the overall design and verification flow.
The idea of AI assisting in the very creation of the hardware that powers our entire digital world. It really is transformative, isn't it?
Yeah.
We're sort of witnessing a shift where the tools we build can now also help build the next generation of tools.
Indeed. It's really a testament to how quickly these language models are maturing and finding incredibly practical applications, even in highly specialized, demanding domains like silicon design.
So wrapping up, what does this all mean for you, our listener?
Well, for you, it likely means that the pace of innovation in hardware could accelerate even further. This could lead to more powerful, more efficient, maybe even more specialized devices appearing across the board, perhaps sooner than we might have thought otherwise.
Faster chips, better gadgets.
Potentially, yes. The ability of LLMs to help distill, human language and high-level ideas directly into the silicon blueprints is fundamentally a profound shift in how we create technology.
A profound shift indeed. This deep dive has certainly shown us how LLMs are moving beyond just software, right into the very fabric of computing itself.
And it leaves us with a really intriguing question to ponder, doesn't it? As AI becomes more deeply embedded, not just as a user of hardware, but as a co-creator in the design process itself.
Yeah.
How will our relationship with technology continue to shift? What happens when the tools we create can genuinely participate in creating the next tools? Will we start to see entirely new paradigms emerge in hardware design? Things that perhaps humans alone might not have conceived of, pushing the boundaries of what's even possible in silicon.
That is definitely a thought to mull over. What does co-creation with AI truly unlock?
Fantastic. Well, thank you for joining us for this deep dive into the fascinating world of LLMs and chip design.
My pleasure.
We hope you, our listeners, feel a little more well-informed and perhaps, like us, a lot more curious about the silicon of tomorrow.